Yes, class. So in the last class, we started with apparent weight. One question we completed. We could complete only one question, right? Principle of flotation also we did. One more question let us discuss. So see, this says that a tank contains water and mercury as shown in figure. An iron cube of H 6 centimeter is as shown. What is the fraction of cube inside the mercury? Fine, this is the question that is given. Now, see one thing, class. When we are just do one thing. Let me draw the figure first also for you. And then you can write it down. Question. See, a tank contains water and mercury as shown in figure. Now, this is the figure given to you. Iron cube of H 6 centimeters is shown. What fraction of cube is inside mercury? So, it's similar to that iceberg question which we did. Just the difference is that at that time, the interface was water and air. This time, the interface is between water and mercury. Mercury water interface is there. So, again, the same thing will happen. See, buoyant force will be upwards. Weight will act downwards, right? So weight will be actually the entire weight will not be just the buoyant force because of mercury. This time fluid is water also. So entire weight will be buoyant force due to water plus the buoyant force due to mercury. Right, class? That time we just had water and air. Now we are having water and mercury. Now you apply. What is the, how do we write the weight? Mass into gravity. This is weight. How can we write the mass? Density of the body, volume of the body into G. Mass into G, mg. We have been doing this by now, you should be familiar with. Then for water. So this is V, volume of the body, sigma. Remember V sigma G. For buoyant force, we discussed this. Sigma is density of liquid. So density of water into G plus again same thing. Density of mercury into G. G will be cancelled, right, from here. Now see, difference in volume will be there. I have just written the same variable. Let's take some separation. Let's take this is X. So this will be dipped inside mercury will be 6 minus X, right? Now I have to write the volume. How will I write the volume? V1, 2, I'll write it. How will we write the volume? Volume is written as how? How much? How do we write the volume? Area is already there, A. This A is given, A is the area. And thickness is given. So area into thickness will give you the volume. Come to the weight of the body. When we are talking about this entire body, what is the area? Area is A. What is the thickness? Thickness is 6 centimeters into density of the body is equal to. Come to volume of for water, just the water portion. Area is A, but the length, the distance that is covered in water, we have taken it as X. Then sigma water plus. Here the length is 6 minus X. So A into 6 minus X into density of mercury. Again, area will also be cancelled. Now we have the value 6 into density of water. This is given as, no, it's not density of water, sorry, density of the body. Let's check this. It's given in meters. So this was 6 centimeters, 0.06 into. Everything is given. Density of iron is 7.7 into 10 to the power 3. 7.7 into 10 to the power 3. X, we don't know. Density of water, so this is 1000x plus 6 minus x into 13.6. 13.6 into 10 to the power 3. Fine. So I remember this answer, just cross check it once. This is 3.2 into 10 to the power minus 2. This will come. But just cross check it once like this. From here, you have to find out the value of x, which was the question. It's an important question. Please write it down. Wherever you are not able to understand, let me know. I'll repeat it.
Ma'am,
Now,
how did we get 0.06?
6 centimeters, it's given.
Okay, ma'am. We converted?
We have converted it.
Okay.
Right? Because SI unit, this is given in meter cube. Otherwise, we would have got it as, okay, this will also be 0.06 then. This will be.
Okay, ma'am.
That's why I'm saying I have not calculated this. This I just remember the answer. So I have written it like this. Just confirm it once while writing. No, confirm this is the answer only. No, because it can happen. My answer which I have, which I remember, that might be wrong. Just confirm it once while writing also.
Ma'am, I'm getting 2.8 into negative into 10 raised to negative 2.
How much? 2.8 into?
2.8, 10 raised to negative 2.
Okay, this is fine. 2.8.
Yes, ma'am.
Someone else also cross it. It would be then 2.2 because I didn't calculate it right now. 2.8. This much in meters, no?
Yes, ma'am.
So, okay, so that would be 2.8 centimeter. Okay. Someone else also should have calculated. Not only Harsha, Martin, Sarah, Alia, three more students are there. Okay, let's start with surface tension now. See, before we start with surface tension, no, few things you should remember. See, basically, forces of attraction you should remember. This is a very easy concept. It's just that for understanding surface tension, you have to have knowledge about this. Surface tension is a very common phenomenon. You'll observe it everywhere. Even in inside of human body, within the lungs and alveoli, you have the surface tension existing, the surface tension all. So everywhere you have surface tension involvement wherever fluid is present. So that's why this is very important. Two types of forces are present. Just understand this. Intermolecular forces between two molecules. These are of two types. One is the force of cohesion, one is the force of adhesion. Just remember, when these two molecules are of the same material, we call it as force of cohesion. If this is one material, this is something else, we'll call this the force of attraction between them as force of adhesion. Now see, take an example. Okay, one more thing that I'll tell you later. First, just understand this. Force of attraction between the molecules of same substances is called force of cohesion, cohesive forces. Forces of attraction between molecules of different substances is called force of adhesion or adhesive forces. If I take a glass, normal, regular steel glass or steel glass I have taken, and I have filled it with water. Now what will I do? I'll revert it. I'll just inverse it. Class, tell me one thing. Just a question for all of you, simple question. When I'll invert the glass, all the water will fall off because of gravity. Just tell me one thing. Will the entire water will fall, or do you think some droplets of water will stick? What happens in real life?
Some droplets will be left.
Droplets will be left. Very good, Sarah. When you invert the glass, even when you throw water from the glass, or even when you drink water from the glass, steel glass le lo, koi bhi glass ho, what do you observe? Water droplets are still left, right? One more example I'll give you. If I take the same thing, no, same example. If I take the same example and I will take, instead of the glass of water, glass I have taken, I have inverted it. Fine. But the material that I had kept here, this was, let's say, mercury. When I'll invert it, no, the glass will be as it is, perfect. Now I'll tell you what happens. Basically over here, there is the force of attraction between the water and the glass and the water droplet. These are two different material. One is glass, the material of the glass. It can be glass, it could be fiber, it could be steel, any material. And one is water molecule. So force of adhesion is existing. Here force of adhesion is greater than force of cohesion. How? Forces of cohesion, these are existing between the water droplets, right? When the glass was filled here, because of force of cohesion, this was filled. So what happened? if water force of cohesion was existing, water should also have stayed together, stuck together. But no, this doesn't happen, because in this case, force of adhesion, this becomes greater than force of cohesion. This was between water. This is between water and mercury. Water and glass. So here what happens, all these water, the force of cohesion is all the water droplets fall off. But what happens? Because of the strong force, some droplets stick. Whereas in this case, what happens? The force of cohesion is greater. So what happens here? In this case, in the second case, all the droplets of mercury which are present, all these droplets, these are stuck together. So they, one by one, chain by chain, linked completely, they fall off. All the molecules which are present, completely chain by chain linked, they'll fall off, because this force is very weak over here. So in this case, force of same molecules like mercury, the force of cohesion is greater than force of adhesion. This is what is the basic application based question that comes in the exam also, and you have to remember. Chalo, surface tension, I'll tell first, write down this. Okay, let's start with surface tension now. Now, what is meant by surface tension? Surface tension is basically the property of a liquid at rest by virtue of which its free surface behaves like a stretched membrane under tension and tries to occupy as small area as possible. This is known as surface tension. See, this means, understand this with the help of example. This is, let's say I have taken a container and within the container, I have kept water. Now what is happening? Water molecules are present here. Right? Water molecules are present here. This is air. So see, what is the tendency of these molecules? These molecules which are present at the surface, free surface, not these depth ones. These molecules which are present at the superficial surface, they have the property to stretch themselves. And then this upper free layer acts as a membrane, and there's a force, continuous force being applied to stretch them. So this property, this force that is being created, that force is called tension. And since it is occurring in the superficial surface of the free surface, we call it as surface tension. Basically, liquid tries to minimize its surface area. This is expanding, this molecule is expanding, but it won't expand. It will try to occupy minimum surface area. So as a result, what will happen? A tension will be generated. I'll write down the statement. Liquid tends to minimize its surface area outside. It will tend to minimize its surface area outside the fluid. Like this is best understood with this example. If you take paint brushes which you have. So the tips of paintbrush, if you will see, this is how the tip of a paintbrush looks like, right? Outside the air. Now, if I'll take the same brush, will it be like this only within the water? Here it is trying to minimize the surface area. What will happen? As soon as it will go on the free surface, tension will be generated because the brush particles will be spreading like this. Right? This happens. Brush, if you put it in water, this is how the hair particles of the brush will be. And as soon as you remove it, it will tend to occupy minimum surface area because of the liquid which is stuck over here. So the property of a liquid at rest, by virtue of which its free surface behaves like a stretched membrane under tension and tries to occupy as small area as possible, is called surface tension. This is occurring because of the phenomena of surface tension. Fine. This you have to remember about surface tension. Now, formula of surface, it's a physical quantity which is equal to force per unit length on an imaginary line drawn on its free surface. What is meant by this? This basically means surface tension. That was physically, but how will you write mathematically? Surface tension is basically force per unit length. This is force per unit length. So surface tension is force per unit length. So SI unit is Newton per meter. This is surface tension. This will be used in your dimensional analysis questions also. A very easy question I'll show you. So this will be clear. A dust particle of mass m remains in equilibrium over a liquid film of length L. Calculate surface tension. It's like liquid film is there. It's like, I'll show you. See, there's a dust particle and this is a liquid film. This is a liquid film as in, have you seen those soap bubbles? Not soap bubbles, those bubbles games which are there. You dip it in solution. They are of various shapes like this, edge is there, or this is made. And when you dip it in the solution, this has a very slight thin film of soap. And when you blow up in air, so bubbles are formed like this. So similarly, this one, this is what I've drawn. Here there is a slight film. Are you understanding this? What am I referring to? Yes or no? Clear or not? Is it getting clear
Yes.
or not? This is
Yes,
a
ma'am.
very slight thin film. It's like a rectangular space is there. I've dipped it inside a liquid, and here a very, very slight film has been developed. Now, what will happen here? Downwards, mg will be acting. Fine. Which will be the force. So force here will be mg. Now, when I'll be using the formula of surface tension, it is force per unit length. So surface tension here will be mg divided by L. Because mass was given, length was given. This is the formula. Like this, you have to apply surface tension. And one more thing, remember. Just remember this point. Surface tension is always inversely proportional to temperature. If you increase temperature, surface tension will decrease. If you decrease temperature, surface tension will increase, vice versa. Some more question also we'll see before we start with surface energy. But write down this first. Okay, these also points. Surface tension is a scalar quantity because it has no specific direction for a liquid. Then it's not simply a force, but force divided by length. See, surface tension physically meaning is force only. But mathematically, when we write, we refer to a unit length. That's why the formula is force per unit length. But physical meaning is force only, the tension that is being produced. And surface tension of a liquid decreases with increase in temperature and vice versa that I have discussed. Write it down from here. Class, this question is a homework for you. Let's start with surface energy. So surface energy basically is the work done in order to increase the area, no, for the
Just roll up
liquid
this once.
surface. Yes, Harsha?
Just roll up this once.
Yes, yes.
Okay, I'm done.
So surface energy is basically the work done. Work done by the surface tension in order to overcome the area. That's what is called as surface energy. So the work done against force of surface tension per unit area in increasing the surface area of a liquid at constant temperature is called surface energy of liquid. Means this surface energy from here, this is surface energy, not surface tension. So surface energy will be equal to work done per unit area. It basically means, no, what? The molecule is expanding, so some work will be done against it. So for the entire liquid surface, if you just take 1 meter square area and calculate whatever is the work being done, that you call it as the surface energy. There is a derivation. This derivation can come in your exam. Not a very, very important derivation. Not a very important derivation. Just have a look while revising. So the question will also be like this: relation between surface tension and surface energy. So consider a soap film having length L of free surface. Having length of free surface as L. It means, let's say if this is it, the free surface length is L. Fine, surface tension is the force. Force due to surface tension if we calculate. See, force due to surface tension, always remember, if it's a soap film, we are talking about soap film. This is one point which I missed while telling you people. Whenever we are talking about soap film has two layers, one here and one on back side. So length doubles. Like we write, no, force will be surface tension into length. Here we'll write 2N. Always for soap, remember, wherever you have written the formula also for surface tension, at this point that for soap, we write the surface tension as force divided by 2N. This is for soap because two layers are there. If you see it from this view, one side like this. But for other liquid, it's just one single layer. So that's why we are doing the derivation for soap film. Now, external force on the soap film that will be occurring. External force on soap film that will be occurring. This external force will actually be equal to this force due to surface tension, right? Now see what will happen. One more thing. See, external force will pull this. It will now reach some value. So let's say some displacement also has occurred. Initial separation was X. Now some change in the displacement has occurred, delta X. Now look, due to external force for soap film displacement occurs by delta X. Here the displacement that is occurring is by delta X. So if this is the displacement is delta X, force is F, work done will be external force dot dx. How do we write work done? Work done is written as no F dot dx. So F external dot delta X. So what will be the work done? External forces, surface tension into twice the length. This is the force dot delta X. This is the force due to surface tension. All right. Now see, when we are talking, delta A is the increase in area. Area will also be increased because here we have to refer to the entire volume. So see, if delta A is the increase in surface area, when I'm writing this 2, I'm just rearranging it. 2 L into delta X, right? 2 L delta X then S. Now length into delta x means length into breadth is actually the area. So what can I write? Work done by the external force will be surface tension into area. Understood? And if we are, why am I ignoring this 2? This 2 is specifically for soap film. So when we are talking in terms of, this is generalized, when we are talking about soap film, that becomes 2 into area into surface tension. This is valid for soap film. Soap bubble, soap film will be mentioned in the question. And this is for generalized. We'll see a question also based on this. But first, write down the derivation.
Ma'am, how did we get force equals S to L?
See, surface tension is equal to what? Surface tension is equal to force per unit length.
Yes, ma'am.
So force will be equal to surface tension into length. Fine.
Okay, ma'am. Yeah. Ma'am, here S is surface tension, right?
Yes, yes, surface tension. Okay. Okay, I'll discuss this question in the next class now. So this completes surface tension as well. Then we are left with excess pressure and capillarity under hydrostatics. Okay, class, you can leave now. Thank you so much.
Thank you, ma'am.